Right, okay, a short one. Let's say that this is a 50 megawatt nuclear reactor designed for submarines, and it's 1 by 1 by 1, right, in size. So what does that mean? That means that the volume of it is 1 cubed, yeah? 1 times 1 times 1. Yeah, 1 times 1 times 1 equals 1. So it's 1 unit of nuclear reactor gives me 50 megawatts. And the surface area of a cube, well, it's the square of each side. So it's 1 times 1, which is 1, times the number of sides, which is 6. So the surface area is 6. So we have a ratio of surface area to volume of 6 to 1. So if this thing gets hot or breaks down, right, it has 6 units of surface area to radiate the heat away before the box that it's in melts. Yeah, so if the thing gets out of control. Now let's have a look. If we scale up from 50 megawatts to 400 megawatts, we've now got a box with 8 of these volumes, right? 2 times 2 times 2 is the volume. So that's 8. Yeah, so you've got 8 units, sort of like eight of these things stacked together in a cube, right? But now the surface area is 2 times 2, which is 4, times 6, which is 24. So we've now got 24 units of surface area, but we've got 8 units of volume. So the ratio of the volume to the surface area is now being reduced to 24 to 8, or 3 to 1. So in other words, as we make the reactor bigger with the same design, the amount of surface area that the box can radiate heat away in the event of some sort of runaway effect gets smaller. So there's less area to get rid of that heat, which means that that box itself just gets hotter and hotter and hotter compared with the smaller one. Everything else is equal. It's exactly the same design, because this is basically what modern nuclear reactors are. Most of the ones built in the 60s and the 70s, which are still in operation all the way through to the early 80s, are all basically some form of sort of pressurised water reactor, and even pressurised gas reactors and whatever you have. They all use a working liquid sort of type of system, right? So which is all a much of a muchness when we're talking this scale. But if we make them bigger for economy, right, which is what the scale is, right? You don't make lots of small ones, you make one big one, right? They become progressively harder and harder to keep the bloody reactor inside the box. So what does that mean? Well, it means that you have to keep the box cool. So to keep the box cool, you have to cool it. So even if you want to switch the bloody thing off, you've got to pump energy into it to keep it cold. Now just think about that for a second. You've made a machine that you have to put energy into to keep switched off. So you're now totally reliant on the cooling systems to take the heat away, because the surface area of the reactor now cannot radiate it away passively. And you've now fallen into what's called in nuclear engineering passive failure mode. You've got no passive failure mode when you compare it with the small one, which is one of the reasons why submarine nuclear reactors have very low rates of accidents or incidents, because the bloody thing's small enough, it doesn't bloody, want to leave the box. Now some of these reactors, I mean, once you get to sort of like, you double the size again, right, yeah, it starts to become uncontrollable if in the event of something going wrong. Which is why, when these things melt down, they literally melt concrete and to turn into a lava. So how did they go about convincing everybody that these things were going to be okay? Well, basically they went on the premise of having layered backups. So you'd have multiple systems, all of which were mechanical, to try and cool the thing in the event that another system broke down. So you take Fukushima, for instance, it had a water cooling system that was run by the electrical grid. So if the reactor was taken offline, you could pump out the cooling water around it using electricity off the national grid to keep it cool. If that broke down, there was then a set of on-site generators, quite capable of replicating what the grid did, that could run for as long as you could put fuel in them. So even if they ran out of fuel after a few days, you could just get a tank of fuel and top it in there and keep things cool. And if they broke down, there was emergency batteries which could keep the thing cool enough for, I think it was about 24 hours, to let you get the generators or the reactors or the grid or whatever it is you need to get in there to get the cooling system going again. So you had these 3 layers. And the thinking is, well, you know, what's the chances of all 3 going? Well, all 3 did go. They had an earthquake and a tsunami, and it knocked out the grid, it knocked out the generators, and the only thing that was left was the batteries. But the fact that there was being an earthquake meant that no vehicles could get to the site, because everywhere was, you know, was hell in a handbasket because of this gigantic earthquake and tsunami. So they sat there and just watched while the batteries ran down, and then the bloody things blew up. Now here's the thing. Every single nuclear reactor in the world presently basically is reliant on these cooling systems to switch them off. Now you can disassemble them and pull the cores out and take them apart into bits, right? But that's quite radical and expensive thing to do, and they're loath to do that sort of thing. And attempts to sort of like drop nuclear moderators, things that slow the reaction down into the core, can have the inverse effect. For instance, that's what happened at Chernobyl. They had this weird design, which meant when they tried to scram the reactor, the thing bloody blew up, right? Because, you know, the engineering is just not quite that, you know, reliant. So now the current thinking on nuclear reactor design of large-scale ones is to create some sort of passive mode for failure. So if you lose all power and all supply, you basically design the thing to melt down into what's called a catcher. So you build the entire nuclear reactor on a giant concrete wok, right, that's buried underground. So when the thing melts, it just melts into the ground and is caught by this gigantic, you know, absurd underground catchment system. And that's not really a passive failure mode. That's really just a system for catching it when you realise you've no longer got this thing, this genie. The genie's out of the box and you can't control it anymore. And that's the current thinking. Now, to make a safe nuclear reactor, you have to make them smaller. That's why these modular reactors, and people go on about, oh, you know, using molten salt. But that's really not, that's not why they're safe. Even though that's one of the things they can use, you know, various types of technology, very clever, blah, 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 right? The reason why they're safe is because they're bloody smaller. Now, this geometric effect of scale, right, yeah, is all throughout nature. I mean, it's one of the reasons why you don't see small animals in the Arctic. Because a small animal has increased surface area compared to its volume, compared to a large one. You know, you don't see many mice, yeah? They get all small birds, right, yeah? You know, they don't tend to fare well, you know, in the Arctic sort of regions, right? Or insects, for instance, another thing. You don't get many insects in the Arctic. I suppose you get krill and things, right? But I mean, this is just a facet of the geometry of space, and you can't get round it. So consequently, if we are talking about using nuclear power on a large scale, you know, to combat climate change, we have to either accept these weird designs where the nuclear reactor is preordained to break down and fall into a nuclear catcher, or is made on a small scale. There's just no other ways around it. You've just got to, you know, no one can build a box to hold a load of a big nuclear reactor. That's it. That's all I've got to say.